Today, we are excited to have Dr. Bryan Kaiser as today's speaker. After a Bachelor and Master of Science in Mechanical Engineering at the University of New Mexico, where he conducted research in computational nonlinear dynamics, he earned his PhD in physical oceanography last December from the Massachusetts Institute of Technology Woods Hole Oceanographic Institution Joint Program. He is currently a postdoctoral research associate at Los Alamos National Laboratory, where he works in the computational physics division. And with that, I'll hand it over to Bryan. Thank you for joining us today.
Thanks, Ginny and Tom, and to everybody for inviting me and having me for this talk. So I'm going to talk a little bit about some recent work on empirical leading order analysis by AI that I've done with my collaborators Juan Saenz and Daniel Livescu at Los Alamos National Lab. So, why is it not letting me change slides? Oh, there we go. Okay. So first, at the beginning of this talk, I'm going to go over the perspective that motivates this work, which is got a dash of opinion involved in it, and so feel free to disagree or debate me on some of those ideas. And then I'm going to just really quickly go over the basics of unsupervised machine learning and then how unsupervised machine learning has been applied to leading order analysis. And then I will talk a little bit about our algorithm that automates the process of leading order analysis of empirical data, show you guys some results, and then conclude. So what I showed on the previous slide and this slide as well are some fluid flows where you have different dynamical regimes based on where you are spatiotemporally, which is the system that is the target for this this particular work. So just to go over some of these buzzwords that I have been all over the news in recent years, and I think a lot of you are familiar with, but there's some variability on their exact definition. So when I refer to machine learning, I'm referring to algorithms that generate some kind of and improves through experience, where experience in this case tends to mean iterating over data in some form. And that's slightly distinct, but overlapping in many places with the concept of AI, which is algorithms that are built to mimic the functions of the human mind. So at the very highest level, you could say AI would be mimicking something like the scientific method, and maybe at a lower level, you could think of AI and machine overlapping in the concept of what a neural network is. And then these two ideas that have, I think, are gaining importance, at least in scientific AI and machine learning, explainability, which is exemplified by AlphaGo, where they have constructed this reinforcement learning algorithm that outperforms the best human player. And then there's this challenge now to understand what exactly it's doing. And so people generate these secondary post hoc models that sometimes are linear and in an attempt to demystify the black box. And to some degree, that raises the question of if you come up with a linear model to explain your machine learning and it works, then why did you do the machine learning in the first place? And Cynthia Rudin recently published a paper, a perspective or opinion paper, about pushing or advocating for this idea of more interpretability in AI and machine learning, at least in science. She's coming from a sociology background. And that idea is that we should be constructing our models so that they're more directly understood by humans. And that's, of course, a domain-specific notion. It's not a rigorous idea, at least not at this point. And to some degree, that's also human-specific because it might be interpretable to a scientist, but obviously not all humans. And so the plot on the left here is from a DARPA report that she points out is actually lacking actual data to back it up. And the basic idea here is that on the y-axis you have predictive performance, And on the x-axis, you have interpretability. So on the top left, you'd have something like an algorithm that can come up with the theory of relativity, but it can't put it in equation form or a paper or a seminar. And then on the, the bottom right, you'd have something like a human scientist. But what she points out is that there's actually not real evidence for this, and that this trend is real, even though it's kind of an assumption that's sort of been baked into the AI machine learning community. So the idea behind this work is to say, let's start at square one and see if we can reproduce basic scientific tasks with AI. So in this case, it's empirical leading order analysis. So on the top left here is a plot of like isosurfaces of vorticity in a turbulent boundary layer that's spatially developing from the front of this plate. And there's a long history of what it took to go from seeing a boundary layer and creating this plot on the bottom right where you have different regimes that are identified, where you have these statistically significant sub-regimes that have different dynamical balances. And this all kind of began with D'Alembert in the, I think, 1700s, pointing out that friction is not very large in most fluid flows that we humans experience. And so in that sense, there should be no drag on a ball when you throw it. And it took 150 years before Prandtl pointed out that actually friction becomes very important in a thin subregime called a boundary layer, which you can then parse even more. And so the process of doing that took a couple of different things. It took the ability to classify the two different regimes, to recognize them as distinct, and then classify them as different flow, different terms being important in the momentum equations. So what we've done applies, this project is to basically do that to any dynamical regime, and it's going to apply particularly where you need to have data, so it's empirically estimated. You have a strong separation of dynamics at many different scales. So in that sense, it's a system you want to approach statistically, which is why we're using this data analysis tool of machine learning and AI. And that there's also some variability in space, so non-asymptotic regimes. So things are, you have different regimes in different spatiotemporal regions. So what is unsupervised machine learning, or I think maybe a less grandiose way of saying that is clustering algorithms. So this is the same clustering performed on two variables with two different permutations of their spatial organization. So if you look at this is the same process in each row, and the left-hand side, left two columns, I have these variables A and B, and in the top row, they're kind of randomly assigned to grid points, and in the bottom, there's these sort of distinct regimes, if you want to think of them that way. And then we run a clustering algorithm on them. This particular clustering algorithm starts by looking at a point in this phase space. So in the third from the left column, you can see that I've plotted the variables A versus B. And so it's looking for where those two variables are close together in this kind of variable space. And you get the same result no matter how they were arranged in the left two columns in terms of labeling each regime, and then you can project it back onto the original, in the right-hand side column, back onto the original data to see, oh, what was this grid point labeled as? What balance was this? So if you look at the bottom right plot, you'll see there's this column of blue, kind of gray blue, and that corresponds to, if you look to the plot to the left of it, where A is about -9 and B is about -6, right? So that's what it's labeling. So it's not really mysterious. It's learning in the sense that there are guesses at where these clusters are. And so, these are effectively, you're guessing at where the correlations are, and then you can find these clusters. So next, I'm going to show, this is an example of when you apply unsupervised learning to something like the barotropic vorticity budget. So Micah Sonnewald and her collaborators used sea surface data, observational data, and to calculate terms in the barotropic vorticity budget, which is shown on the bottom right. And then they ran a clustering algorithm, and it picked out dynamical regimes that oceanographers are familiar with. So this kind of white-green area, which has the arrow going from it, corresponds to this plot on the right, which is showing a sphere drip type balance between your planetary vorticity and wind stress curl. And then the other terms in the vorticity equation are very small. I guess you could, if you look at the y-axis there, you could say they're at least an order of magnitude smaller than the sphere drip balance type with the other terms. So there's a couple of things here. So if you want to go to actually getting rid of this terms in the equation, you then need to classify the top right plot and say, okay, when can we throw away these three terms that are on the right-hand side of that plot that are small? So Callahan and authors came up with an answer for that and tested it on various different flows and different dynamics. You can see they did a bursting neuron. They did an optical example, a GFD, boundary layer, a cylindrical wake. And basically they generated some sparsity in that equation, meaning they threw away terms. They assigned terms 1 or 0, off or on, by coupling the clustering, same kind of clustering that Sonnewald et al. Did, but then they added in this SPCA, which is a method for generating sparsity based on combining PCA and something like lasso regression. So for those unfamiliar, PCA, principal component analysis, or some people call them empirical orthogonal functions, they're basically a way to take data and decompose it into orthogonal modes that are sorted in order of the amount of variance in the mode. And so what they do, Callahan et al. Did, was to say, let's apply that to the equation space data for, say, the barotropic vorticity budget or something like that. And we will then do the regression, this lasso regression, on the principal axes. So the principal axes from PCA point in the directions of the most variance. So if you're looking at your clusters, you could think about it where the clusters are going to be spread or fatter or things like that. And so there's a legitimate reason to do that because you're taking into account the shape of your cluster. However, the hard part here is that they want to set some terms to 0. And when you use a lasso regression, which is like a weighted least squares, it introduces another free parameter, commonly called alpha, and you have to tune that. So now we've got to tune our parameters in our machine learning or in the unsupervised learning algorithm, and we've got to tune the free parameter in our lasso regression. And so what I'm showing here on the right-hand side plot is if you're trying to fit to these blue dots, some of these cases where will match, the line fits the data pretty well. But if you turn alpha up too large, you get the pink line, which is skewing from the data, I would argue. So you have a free parameter that you have to choose correctly, and you also introduce a little bit more stochasticity in the sense that you have to do a minimization to get this. So at this point, does anyone have any questions? I just want to check. Or is everyone can hear me?
I don't see any questions in the chat box yet.
Okay, great. Feel free to interrupt me. Okay, so that's basically the state of the art on how you would take data and sort out which equation terms are leading order just with an algorithmic approach without a human involved. So this is kind of this plot here. I'm trying to break all this down into different tasks. So in the left column, you see what I mentioned before, where historically what a scientist did at around the year 1900 was they'd recognize, okay, we've got different parts of our dynamics that look like they're in different regimes. And then they say, okay, I'm going to scale the equation terms and try to throw away terms in different regimes. And if you break that down into tasks, the first would be you're going to partition your data with clusters. And then you're going to define a characteristic feature vector for each cluster. So we have a simple way of doing that. We just take the average value. So our cluster identifies 1,000 grid points. We'll average over those 1,000, maybe wait for area, et cetera, to get a characteristic mean feature vector. And in this case, the feature vector is the equation terms. So you're going to get a mean equation for each regime that's been identified in one. And then you have to define what we call a hypothesis, which is just saying that we're going to assign equation terms a 1 or a 0, on or off. And then the final step is to test that hypothesis, which is to say, how well is it fitting the data? So if you go to the right-hand side column here, we start out with a clustering algorithm that partitions the data. Then we do something to identify the clusters as zeros and ones, and we agglomerate clusters that have the same pattern of zeros and ones, the same sparsity pattern. And you can do this, either one of those, you have your choice of algorithms. And then finally, how well does that actually fit the data? Let's test our hypotheses. So that's what we call this score, which is something that we're certainly not the first ones to develop a score for unsupervised learning. They've been around for as long as unsupervised learning has been around. And it's basically a way to tell how well what you assigned is actually fitting the data. And so I'll talk really briefly about the magnitude score. Yes.
Can I just ask a question, because you said it would be okay to interrupt? Could you go back
Sure.
one slide? I'm still stuck a little bit in the middle column on number 3, the define a hypothesis. Could you give an example of what this hypothesis would be?
Yeah, that's a great question. So a good example of that would be, let's say I'm looking at a turbulent boundary layer, and I'm gonna make a guess based on the data that I've looked at that the mean flow and the Reynolds stresses have a balance in the outer boundary layer. And so that would be an example of a hypothesis. And that would translate into, if I had my boundary layer equation, Reynolds averaged, those two terms being leading order. So does that make sense?
Right. So the hypothesis basically comes from the domain expert looking at the output of number 2 with your clusters and kind of then coming up with a hypothesis which then you're going to test. Is that right?
Traditionally, yes, but that's what we're trying to replace. So with SPCA, it's going to take the equation, and based on the PCA principal axes, it's going to throw away terms. So it'll automatically identify those two terms.
Got it. Thank you very much.
No problem. So really quickly about this magnitude score, I'm not going to get into the details because it's kind of tedious, but the basic idea is that we come up with this score to tell us how well we've actually fit the relative order of magnitude separation in the data. And we can use that to identify clusters, but we can also use it to optimize the whole algorithm, the clustering algorithm, and the choice of your sparsity pattern or equation terms you're going to retain. So the basic idea is, let's take this example feature vector. So at the top, you see x is equal to the zonal momentum equation and a Boussinesq flow. And it has 9 terms. So the indices of the full set I are 1 through 9, and then J would be the indices of some subset that we're going to choose, which is some combinatorial of I. And the basic idea is that the magnitude score is the product of 2 variables, R, which is a ratio of the sum of log 10 of the absolute relative differences between the largest absolute maximum value in the set in the feature vector X, and B, which is a bias factor towards selecting smaller sets. So we added B because if you just use R, it's always going to tell you to choose all of your terms. And B is this reflects a bias that we want to be able to throw away some terms. And so I'm still in the process of breaking this and seeing the flaws in it. But basically, what happens is there's a limit on the bottom right of R that as the terms that you neglect as the sequence product of the relative differences, absolute relative differences of the terms that you neglect, as those get very, very large, then that sequence product goes to 1, and that drives R to 1, which effectively gets you to your optimal score. And then the bias factor, I won't get too deep into that, but this has some nice properties. So M is bounded by 0 and 1, 0 being not a good choice and 1 being the best. And there's this full set score. So in the middle bottom right, the MXI, where I equals J, that's just saying that you've chosen all of the terms and you get a score that's in between 0 and 1 that is the full set score. So basically, there's 2 choices here. When you calculate this for a given feature vector, it's either going to be above the full set score, which means you can throw away terms, and that is merited by the separations of the order of magnitude separations between terms, or it's going to be less than the full set score, in which case you should keep the full set because it means that you're losing something. And finally, in the bottom, you can multiply your feature vector by any constant. And so you don't have to non-dimensionalize your equations. You can just put them in as they are as long as your units are correct. So an example of this, let's take a typical ocean basin scale parameters, and we can estimate the scales. You can see at the top here, X is equal to the scaling for those terms on the previous slide. And then we get these numbers on the right below that when we do that scaling. And we immediately see, okay, the 2 largest terms correspond to geostrophy here. So if you then calculate the magnitude score for every possible combination of terms that you could choose out of X, what you get is the middle plot the bottom left plot. So what this is showing is that the blue triangle represents where geostrophy is the 2 terms that you're keeping. And you can see that on the plot on the right, where on the x-axis is the terms and on the y-axis is the score. So it's not exactly 1, but it's approaching 1, and it selects Coriolis and pressure gradient balance. And then the next best scoring are these purple squares. And when you look at the plot on the right, you see, okay, that's geostrophy plus 1 term. And then I didn't check it, but I assume the staircases in the gray dots are plus 2 terms, plus 3 terms, and so on. And then the black line there is the full set score. And when you look at the bottom of the plot on the left, there's a gray line that's actually a bunch of dots. And those are all the permutations of X where you didn't choose one of the 2 Coriolis terms. So it's got a low score. So that's the basic idea of this magnitude score. It's based on taking the log of absolute relative differences. So if we apply this, so let's say, okay, we're going to cluster using a Gaussian mixture model, which is just a fairly standard unsupervised learning model. And then we're going to identify the which terms are kept in each regime with sparse PCA. And then we'll optimize over the SPCA and the Gaussian mixture model free parameters until we get a result. So this is the same method that Callahan et al. Did. And the equation, the boundary layer, Reynolds average boundary layer equation is shown on the upper left. So we have 6 terms. And then on the top left plot, what you see is with error bars is the mean feature vector for each cluster. And so this is what we're then scoring, which is shown on the top right. So on the right-hand side axis of the top right is the scores for each cluster. And so what you get are things that are familiar to boundary layer engineers and scientists. So the bottom two with the very high magnitude score of 0.96. There's this gray circles represent a balance between Reynolds stress and mean viscous diffusion. And when you look down at the bottom plot, you see, okay, that's labeling this bottom area as gray, which makes sense. That's where we expect those two terms to be large. And then in the cluster 1, immediately above that, the light blue stars, that's this sort of light blue region in the bottom plot, which is where you expect there to be this inertial subrange of a mean flow balancing with the Reynolds stress. And then, of course, on the bottom left of the bottom plot, there's the kind of a hodgepodge of clusters, and that's reflected by the fact that transition is a very dynamically difficult problem. So we get very similar results if we do this again, but now instead of identifying the terms with the SPCA, we've identified by just doing combinatorial search over all of the possible permutations of terms you could select and scoring them and just taking the best score. So that could be optimized because obviously it's exponential, and you don't, if you have 100 terms in your equation, which I don't know how many people do, but maybe that does come up, then there's a little more work that we need to do to address that. But by and large, we get very similar clustering, and we also get similar parameters that it tunes. When we loop over all the clustering parameters and all the, and in this case, that's all we have to do, and then it selects something very similar to the other problem. And so to analyze this, how robust this is, I went through the same problem and calculated the balance that the magnitude score selects at every grid point in that flow, which I'm calling the truth. It's not actually the truth. It's a kind of subjective idea. And then I went through and took for each of these different clustering results and different cluster identification algorithms, I'm showing that at binning by grid point where they've been labeled the same way with the same balance. And it turns out that for all of these, 80% of the samples wind up in these top 3 bins, which are basically, you have some inner boundary layer, outer boundary layer free stream flow. And so that shows that this, is doing what it should do. A score should enable you to identify something in the data in a robust manner. And so now if I switch to a completely different example, which is also new to me, my background is in fluids and geophysical fluids. But just to illustrate that this works on any PDE that you might approach. And to that point, there's something I should mention, which I don't show here, is that you don't necessarily have to know the equation first. It can apply anywhere where you can estimate terms and even terms that you have invented or you're hypothesizing, and so the growth of some variable. So in this case, all the equations I've talked about so far that I've run this on have closed, but there's no restriction in the AI algorithm that the equation close. However, if the equation doesn't close, that does create a new problem in the sense that, okay, you might find that one growth rate is more significant than another, but if your equation doesn't close, you have, you don't know what the residual is. So that's a different problem, but I just wanted to say that there is no requirement that you know the equations. It's just so far, the only way to use this in a productive way is, in my mind, is if you know the equations, but we could be wrong. So here you have a set of 3 equations, and the top one is the one that we're going to run the AI algorithm on. And you have basically a tumor cell evolution equation, and there's and how the tumor cells are going to propagate through tissue. There's a diffusion term, and then there's a nonlinear diffusion term based on this variable f, which is kind of like tumor food, I guess. There's probably no molecular biologist here to correct me on that. But so when you run that, you get results that look like these plots. And when we run the AI on that particular problem, then what you get on this top equation is in the top right, you get these clusters identified. And so what you see is that the projection of the gradient of tumor cell density onto the gradient of the tumor cell food, that term is small in all of the clusters where the tumor growth is actually happening. And so to me, that indicates that, this automatically found that you could throw away that term. And yes, there are simple ways to do this, but the idea is that, I'm doing this on small data sets, but there's no limit to the data sets you could apply this to. If you're going to apply it to something that's very large, then I think this might be maybe a little easier to do than going through this with some other method. And so there's another point to be made here. When you look at the top right plot, the cluster 1, which is labeled with the 2 light blue stars. So for an equation with 4 terms, the full set score is 2/3. So that particular cluster scores poorly relative to the full set score, which means that in practice, that cluster would just be labeled with all the terms. So that's kind of, and when you actually go through and look at the data, what you see is that it's happening where the tumor has already grown and is in some sense kind of static. So that's another caveat to the way that this needs to be applied, is you have to just add in an if statement to switch any low scoring cluster to the full set score. So with that, I'll conclude with just basically the idea that we've put this together in such a way that now leading order analysis, or empirical leading order analysis, can be formulated as an optimization problem, and is no longer something that a human necessarily has to do, which is useful, in a lot of studies, like in particular in the tumor dynamics study. They had the authors that I followed their equations from. They had several papers in which they turned different terms off to estimate which term was the largest or which term mattered more, and then they recalculated. So the idea is that by doing empirical leading order analysis for you, that automates that part of that study, which took them a lot of time. And the second point is that you don't necessarily need to know the equations you're doing this for, but you would need to have some idea of the residual of terms that are not being identified for this to actually be useful. And with that, I'd like to thank you for having me today, and I'll take any questions that you guys might have.
Thanks, Bryan. So let's take the next 10 minutes for questions. If anyone has any questions, use the raise your hand button. I'll call on you, or you can type your question into the chat box. All right, there's the clarification from Ime. Is the best paper on this topic the Callahan paper you cited?
Yeah, well, they're the most recent, and they include the SPCA method. Yeah, the Sonnewald et al. Paper, they don't go that extra step. So it's the most comprehensive papers to date. Although we're trying to get this out the door, so it should be published fairly soon.
All right, a question from Mike Pritchard. Go ahead.
Hey, Bryan, thanks for an interesting talk. I remember seeing Micah Sonnefeld speak about her work a year ago or so, and the tension came up of center we just spheres balance or confirming our notions of what these clusters should look like versus opening up new questions with this toolkit. And in her case, I think there was an argument that the of the interfaces between these boundaries of balance were hard to detect without these methods, and that is a form of new question that becomes open up. What sets the scales and the shapes of those boundaries? In your talk, I was sensing a similar theme of mostly reconfirming notions that we should expect in engineering and boundary dynamicists of the turbulent flow. But what's your outlook on new questions being opened up, or are you excited on that front?
Well, so that's a really great question. I'm not actually, I don't have a great target for off the top of my head, but I think what we were trying to do in this was also to kind of complete the picture with what Micah had done in the sense that we removed the human intuition from it. So we completely removed that aspect from what she had done, and also the Callahan et al. Group, where now you don't need to look at it and say, oh, that looks good. So that's going to be a test of this, is when it gets applied to something where we don't know the dynamical balances ahead of time. And I'm not sure where that would apply, other than I know there's loads of satellite data coming in all the time. And so I anticipate that in the earth sciences, that would be a place for it to go. And then the other future direction is like what I mentioned at the beginning, that towards building more interpretable models. So the idea would be that you could effectively have an AI algorithm create a turbulence model or something else like that would then get used in a subgrid closure in a climate model or something like that, where you have enough data about this particular process. Maybe it's like internal wave breaking or something, and then you can run this AI algorithm that would identify important terms and places in space, and then it would, of course, then have a second algorithm that would then generate a closure using what is done here. So there's a couple different directions where it could go. Yeah. Thank you.
All right, another question from Ime. You mentioned satellite data. How about using this to better model rapid intensification?
Sorry, I meant of tropical cyclones.
Oh, yeah. That's a great question to which I don't have a direct answer for, but I think it would depend on the quality of the data for that intensification. If it was really well resolved, then and you're looking to predict a growth rate, then this could be useful in throwing out terms and picking apart. If you have a lot of data to go through on that particular problem and you want to find a growth rate, then this would be useful for that. But I don't know the details of that enough to really comment very thoroughly.
Thank you. So how can we, once your paper comes out, how will we find out about it?
That's a good question. We haven't quite yet picked a journal for it, but we were thinking something more generic AI journal to try to reach the broadest audience. But that's kind of a question because it's at a weird intersection between a lot of fields that deal with highly nonlinear chaotic systems with lots of data. So yeah, I'm not quite sure. I can try to be in touch. I could do that.
That would be great. Maybe just send it to this working group, and then
Sure.
we can propagate it further.
Yeah, for sure.
Any other questions for Bryan? All right, I don't see any movement in there. So I think maybe we'll end the open portion early and we can hop right into the closed portion. So thank you, Bryan. So this will conclude the open session of today's webinar. And as I said earlier, recording will be shared later. Coming up in 2 weeks on November 23rd, we will have Christiane Jablonowski of University of Michigan. Her talk is entitled Evaluating Machine Learning Approaches for Physical Parameterizations and a GCM Model Hierarchy. So until then, feel free to reach out to me if you have any questions about US CLIVAR or the working group. And thank you everyone for joining.